In this lesson, we're going to try to do something that's kind of hard for me to even get my head around, but that doesn't mean we shouldn't try to do it. You see, we're going to try to make some models about the space and solar system that surrounds this planet. And when we think about the solar system and space beyond, we have two problems. One is that things are really far apart. And two, things are really big. And it's hard for us to have a reference to these things that are big and far apart because we're used to things being in the size that we understand, mountains and buildings and trips on vacation. But when you talk about the solar system, you have to really expand your reference point and try to think of things bigger. I tell you, I still today like to think about these problems and try to figure them out. And it's still hard for me to understand how big is space, how far away are things, and how large are things. But we're going to try it in this lesson. We're going to make two different models. Scientists make models to help them better understand things that they can't go to or touch or hold or feel. So I think that after you do these two different lessons on models of the solar system, I'm going to start to maybe stretch and expand what you think about when you look at the sun or when you look at the stars or the moon up in the sky. Let's get started, shall we? When you look up at night and you see these stars, it's hard not to wonder that space is a large place. But you know, we have visited some of the planets, and we've actually visited our sun, which is a star. This is a picture of the Helios 2 probe that in the 1970s was sent to the sun to see and to orbit the sun and to study it and send us back some information. So we've visited our star. We've gone around it with spaceships. In fact, every year we go around the sun. We call that an orbit or a revolution, as the sun is the center of our solar system. That's why it's called solar. The sun, or El Sol, or Sol, is the name of our star. Let's take a look at this. For example, if I drew, and it's hard to draw a scale, we're really talking about scale, but if this is the sun with sunspots and storms and whatnot and energy that's coming out of the sun, there's all kinds of energy that comes and radiates from the sun: visible light, heat, ultraviolet, X-rays, gamma rays. And all of this from our sun, which is a star, which is, we can call it Sol, solar system. All of this gives life to our planet. And it's big, it's huge. And if we, and this is not going to be to scale this distance, but if this is the sun, the Earth would be maybe not even that large. Because I'm telling you, the distance from the Earth, which is here, to the sun is quite a distance. As we revolve around or orbit the sun, if I can draw this drawing, the average distance to the sun, just the average distance to the sun, is about 93 million miles. Now, usually in science I use kilometers, but today I'm going to be mostly talking about miles, and don't forget to put your labels whenever you write a number. 93 million miles. But since the Earth is moving and it's not in a complete circle, sometimes we're a little closer, sometimes a little farther away. And that's going to be evident in anything we talk about, since everything in the universe is either rotating, expanding, contracting, or spinning on its axis or revolving. It's hard to know exactly at one particular time how far something is. Well, let's take a look back at this Helios probe, the fastest spaceship or satellite that we have ever made. In fact, this probe, when it was in 1976, it was Helios probe 1 and 2, when it was headed towards the moon, when it was headed towards the sun, it reached a speed of 157,000 miles per hour. 157,000 miles per hour. Now, that's pretty fast. That is the record of anything we've ever sent into space, 157,000 miles per hour. But if we do a little bit of math here, and if I get my calculator and just a little bit of math, and if we, let's see, here's my calculator, and if we take 93 million miles, there's 93 million miles, and we divide that by 157,000 miles per hour, that's going to give us a big number, 592 hours. And if we divide that by 24, that's going to give us, let's see, 592 divided by 24 is going to give us days. And so basically, we have, it took about 20, if we went straight, it would take about 25 days to get to the sun. And that's a long time. Going at that speed, it's amazing. Things can go fast in space. There's no atmosphere to slow space vehicles down. That's why they can look in the shape they look. They don't have to be aerodynamic. They do when they're in the atmosphere of the Earth. But things go fast, and things are, well, check this out. If you look at the sun compared to some of the other planets, we have a diagram here, and we have Earth this size, and Mercury, which is very close, Mercury and Venus and Earth and Mars and Jupiter, a gas giant, and Saturn, Uranus and Neptune, and some people have taken Pluto off, but even Pluto, we are all small compared to the sun. It's the sun's gravity that keeps us together. The sun is much bigger than the planets in our solar system. And that's hard to understand because we see the Earth and the size of a small little dot compared to the sun. You see, the sun looks so big in the sky that you might think, well, it looks only that large in the sky, but we're so far away that the closer we get, the actual size of that sun becomes apparent. Now, the light coming from the sun is pretty interesting because it's traveling pretty fast. Now, this is another hard thing to understand. And so, if we go back to our diagram here, the light from the sun, the visible light, travels about 186,000, there's 186,000 miles per second. Wow. 186,000 miles per second. From the sun to the earth, if we did that in kilometers, there's a picture of the sun and the earth, and as you notice, they're not to scale. The sun is not that large compared to the earth. So, and a lot of times when you look at pictures and diagrams, you got to realize that the sun is much bigger than the earth. But we couldn't put them both in this picture. So if you do the math, it's about 500 seconds. And if you divide that by minutes, it takes light from the sun about 8 minutes to get to Earth. So even traveling the speed of light, it takes 8 minutes to get from the sun to the Earth. And that's a long time. Now, we have actually been to different places, a few things in the solar system. We've sent something to the sun. We've sent things to the moon. We sent Voyager out of the solar system. And we have landed on Mars. Let's take a look at some of these enormous journeys. And I got this from the NASA website, but check it out. The time to reach our nearest stars, and this was just crazy, but if you were going by car, it would take you 50,000 years. If you're going to the moon, it took them 3 days to get to the moon. And it would take, if we were going 137,000 miles per hour, it would take us 80,000 years to get to the next star system. 50 million years by car. I mean, it's just crazy. There's, like I said, today we're trying to stretch our mind how far things are and how big things are. we have been to Mars. Now, Mars is another planet, and let's move it out here. Mars. Now, it's really hard to tell exactly how far we are from Mars because, you see, these planets are not in line, they're orbiting. But we have sent rovers and different spaceships to Mars. This is a NASA drawing of Mars, the red planet. You can see a great canyon there and different craters, and there's one of the largest known mountains in the solar system is there. And this is the Curiosity rover that's on Mars right now. We have sent several space vehicles to orbit Mars and to actually land on Mars. Scientists think it would take about 300 days to go one way to Mars if we sent astronauts. And I don't know if I'll live to see that. I hope I do. But you might. You might live to see that. Astronauts on Mars. 300 days there. Do some time on Mars and 300 days back. So it would take a considerable amount of time. And even though Mars, and we'd have to do it at the right time because any given time Mars is, well, it's about, let's see. Mars is about 140 million miles on average from the Earth to Mars. Now, you got to understand that we'd have to go at a time when we are close to the orbits. All right? But, so we have been to the Sun, we've been to Mars, but there's one other place that we've gone to and landed on 6 different times. That's a little bit closer to home. It's in our neighborhood, and that is the Moon. In the late 60s, 1969, and in 1970 and 71 and 72, we landed 6 different times on the Moon, and 2 astronauts on each trip explored the surface of the Moon. And since the Moon is one of our closest objects in the solar system, there's a good chance we could go back to the Moon. The Moon is about 238, let me have to zoom this up again a little bit here, 238,900 miles from the Earth. But even at that distance, and that's that distance right in here, even at that distance right there, it took the Apollo astronauts in their command module and lunar module 3 days to get to the Moon. They did their EVAs and 3 days to get back to Earth. So what I'm trying to tell you is that things in the solar system are big and far apart. This is a picture of the Mars Curiosity rover that's right now on the surface of Mars, making discoveries, taking pictures, doing experiments. And it takes several minutes for radio waves to get there to tell it to move, turn, stop, photograph. Pretty cool stuff. So when you see a picture like this of the Earth and the Sun, with the Earth being right here, it kind of makes us stop and think about how precious and beautiful this planet is. We're the right distance and the right size from the Sun, too much closer to be too hot, too much further away, be too cold. And it's a pretty amazing thing to realize when you start thinking about the size and how far we are. In fact, the Moon looks so big in the sky, but if the Earth were hollow, 50 moons would fit inside of the Earth. So the Moon is about 1/6 the size of the Earth. The Earth and the Moon are different sizes. Well, I'll tell you, there is one more thing, and this one will probably really mess you up a little bit. It does me when I think about it. But look at deep space, and if we can try to find out how close is the closest star, when you look up at the sky, how close is the closest star? Now, this is not an easy math problem to do, and I'm going to have to use my calculator for this, but it is something we can try to understand. So let's try it, shall we? The closest star is called Proxima Centauri. Proxima Centauri is the closest star to us. Now it is 4.2 light years away. 4.2 light years away. Now that, crazy. Let me put that up here. So 4.24 light years away from us. So I'm going to put a star up here. We're going to call that, let's go ahead and call that Proxima Centauri, and from the Earth. And so the question is, and this is not to scale, so the question is, how far is 4.2 light years away? Well, let's see if we can do that. So light travels, if I zoom in on this, light travels at 186,000 miles per second, okay? If I multiply that by 60, I can find out how much light travels. Let's make this light like a flashlight maybe. Times 60, let's see how far it travels in a minute. Well, that's 160,000 miles in 1 minute. Okay, that's miles per second. Now, if we multiply that, that's minutes. We multiply that again by 60, because let's see how many minutes are in an hour. Okay, so if we do that, we can get something like this: 669,600,000 miles in an hour. Wow, that's a lot. 669 million miles in an hour. Well, there's 24 hours in a day, so let's multiply that by 24. And I use my calculator, and you can try this. It gets crazy, but I get, now we're at hundreds and thousands and millions. Now we're going to get into billions. 16 billion, 70 million, 400,000 miles it will travel in 1 day. That's crazy. In 1 day. That's how fast, that's hundreds, thousands, millions, billions. We're into the billions. I'm going to put a B right there. But you know what? There's about 365 days in a year. And remember, we're talking about light years, how fast light will travel in a year. So I'm going to multiply that by 365, and I'm going to get, the first time in my life, something that is 5,865,696,000,000 miles in a year, in 1 year. And remember, if we want to go to Proxima Centauri, the closest star, it is not 5,865,696,000,000 miles away, trillion, billion, million, thousands, hundreds. It is actually times 4.24 light years, which will give us a tremendous number, which I can't even understand, but we did the math. 24 trillion, 870 billion, 551 million, 40,000 miles to the next star. Now, remember that spaceship we did? Remember the Helios 2 probe that went 157,000 miles per hour, the fastest one? If we divided it by the fastest rocket we have, miles per hour, if we did that, it would still, and I did the math, it would take 18,083 years to get to the next star. 18,083 years from the Earth to the next star. So, NASA and other scientists think that we have really only two choices to go in the next future of what you might end up being an astronaut. And that is, we could go to the moon, Mars, we could go to the moon, Mars, or nowhere. It's just too far. Luckily, we have telescopes that can see light coming, and luckily we have science models of how far planets are and how big they are. And so what I want you to do now is get ready to do this lesson, because we're going to make two models to try to expand our minds and see if we can look up into the stars and think about and comprehend how big they are and how far they are, even in our own solar system. Let's get started. So here's what we're going to do. On this lesson, which is making a solar system model, you're going to have groups of students, and what I'd like is we have 6 groups. Now, I would divide the groups like this. I would put one group in charge of 2 of the planets, Mercury and Venus. So you'll make 2 different strips because they're smaller, okay? Another group does Earth and Mars. They're smaller, all right? And then have a group do Jupiter, a group do Saturn, a group do Uranus, and a group do Neptune. And there's a scale right here, and I love this scale. The scale is 1 centimeter on paper equals about almost 2 million kilometers, or 1,940,000 kilometers, okay? So as you see, I would like you to do this. I would like you to put the name of your planet, write the scale, which you have right here on your book, write the scale on your strip, and each meter mark off and label 1 meter, 2 meters, 3 meters. And as you can see, some of you, for example, I think Neptune is going to be 23 meters long. All right, so let's have in the hallway, I've arranged for 3 places for your class to start measuring and taping down the model strips of the planets. On each strip, the name of the planet, mark each meter, and the scale. Let's go check it out. In just a moment, we're going to do the second part of these models. And this one, I'll tell you, well, this one's going to be pretty amazing. So let's get ready to do the sizes of the planet. You'll find that on page 192. Using for our planet diameters, that means how far across the circle of the planet is, through the center is 1 millimeter equals 1,000 kilometers. So that's a pretty big but different scale. The scale is not as big as what we used in our last model. And what I really like about this is there's a simple way to do this, all the materials, but I've added a little bit of change to it because I really like these outer planets, these giant gas planets that you see right here. This is Jupiter, the great red spot of Jupiter that I've been told is the storm is so large that our Earth would fit inside of it. And this storm has been going for over 400 years. I believe Copernicus actually saw this same storm. That's pretty amazing. That's pretty amazing. Here's what you will need. So each group needs the cardstock template, 1 plate, 4 paper towels, sections, a toothpick, scissors, and a ruler. This, a template, into something like this, which eventually will be cut out into something like this. Doesn't that look like the gas giant rotating and revolving? Well, I think it does. All right, so teachers, I'm going to show you how to do this, and then you can work with your students. First thing we're going to do is to cut out the template. I'm going to rough cut them. I want to cut them, for example, I'm going to cut this, these 2 planets apart and just leave it square So I'm going to cut, and just do this with me, just the teachers. Boys and girls, you get to watch here how we're doing this. There's one cut, two cuts. Now I don't know which planets these are. You're going to have to use your book and the scale to figure this out when we're done. Three cuts, four, and let's leave these smaller ones together, okay? So I've cut this into 1, 2, 3, 4, 5 sections. Five sections. The next step is pretty interesting. We're going to use shaving cream. Now, shaving cream is hydrophobic, which means hydra means water, phobic means it pushes away, it's afraid of. So in the morning when I get up and shave, my beard grows at night, and so I put water on my face to soften my beard, and I put shaving cream to hold the water in, because the water won't go into the shaving cream. And then I can use my razor because it reduces friction, and I can get a nice clean shave. We're going to use the chemical properties of shaving cream and the water-soluble properties of food coloring to make some pretty cool designs. All right, so teachers will take care of this. The teachers will do this in just a moment. Go ahead and shake your shaving cream, and we're going to add a small layer onto your paper plate. It looks like this. Now you don't need a lot because it volumizes, which means the gas in it expands a little bit, so that's probably enough. Okay. Go ahead and try that. After you have this and it's volumized, take your ruler, and I'm going to try to make this nice and smooth, a nice smooth palette. Okay. And it's not perfect, but I'm going to try to be nice and smooth. Okay. There we go. That's close enough for the planets. I'm going to go ahead and wipe off my ruler. So I made this kind of smooth. Remember, I said that food coloring is water soluble. It mixes in water. So that means it won't mix very well into the shaving cream. And we're going to use that characteristic to make a cool design. Your teacher will come by and put 1 or 2 drops of each color. 1, 2. That's all we need to put for that color. 1, 2 blues. Now, food coloring will get on you and stain you, so if you follow these directions, we should be just fine. 2, not much more than that. And if you need more food coloring, let me know. Here's some red coming. Okay. Go ahead and add your food coloring, and you notice it stays on top. It moves out a little bit, but it stays on top. It's kind of interesting to look at. Check it out. Add your food coloring. This next part, I hope you pay attention to, because if you follow these directions, you'll get some pretty interesting designs. And if you don't, it'll be kind of like Venus, the kind of cloudy, messy planet. Let's check it out. I'm going to take my toothpick and I'm going to make a few simple swirls, just a few. And just a few, I'm not going to stir it up much, because this will start to stir. You'll see what I mean, but I'm just going to put a few swirls on here like so. Just a few, because the food coloring is still there and it's going to get mixed in quite a bit. Now, if you want to dot around like that, but do not swirl it all up. If you swirl it all up, it's going to be this huge mess. Okay, so the teacher's doing this one right now, and I'm pretty satisfied with that. You can see some really interesting swirls in here. They're going to get really interesting here in just a moment. So go ahead and The first time you do this, less is best. Okay, now is the fun part. If you can imagine that that food coloring is on top of the shaving cream, not mixed in, I'm going to press my planet down like this. This side, I'm going to turn it over and press it down. Go ahead and try that, just one of you. And now when I lift it up, give it a second, I'm going to have a lot of food coloring stuck on my plate right here. And what I need to do is get my ruler, and I'm going to scrape this across a couple times, across in the same direction. In fact, let me move this out of the way. I'm going to lay down a paper plate, or I'm sorry, a paper towel right here, and lay this down. And now I can smear that across like that. Smear it another time. Every time you smear it. And now we still have a lot of cool colors on here, so don't smear it too much. Go ahead and smear it a couple times. See how I have it on a napkin? I'm going to take an extra piece of my napkin and kind of wipe off the extra. And it wipes right off. Set this aside to dry for just a second, and you have a really cool design. But more importantly, you still have a lot of color both on your plate and on your ruler. So you can take another one of these, and somebody can do the plate while another person does this. Now that gets a nice smear on it. Kind of cool. And the more you do it, the more the colors get mixed. So I'm smearing it on there like that. Use my napkin to wipe it off like that. Look at that cool planet. Is that cool or what? And you can actually just go ahead and if you want, stick another one of these down in it here like this. Scrape it off. So teachers, go ahead and have some fun with this. Once you've done all your planets, let them dry, cut them out, and after you cut them out, you can use your book to determine which one is Jupiter, which one is Saturn, which one is Uranus. In fact, it's kind of cool to find out which planet is scaled to which of these different shapes. And if you like, you can probably even put them out in your solar system in the hallway. Kind of cool. Good luck with this. Don't mix it all in or it turns into like this green mess, and don't get it on your hands. You can help it. The leftover stuff makes some really cool designs. Have some fun. But gentlemen, I don't recommend food coloring and shaving. You'll end up with a rainbow beard. I'll see you next time.